So we're going to look at another pattern in expressions that will help us factor them. On the first page, we looked for something in common for all three terms or all two terms. Here, we're going to look for a pattern of two terms connected by subtraction where both of them are perfect squares. And in a case where we see that, we can take that expression and factor it as so. So before we start looking at that, we first have to know, well, what are our perfect squares that we're looking for? So here are, in these square roots, the perfect squares that we will look for, and then their square root, or what we get when we take the square root of them, is next to them on the right. For variables, basically, any expression with a variable where the variable is even is a perfect square. The variable piece is a perfect square. So examples would be x to the fourth, or x squared, or x to the fourth, or x to the 10th. When I take the square root of them, we divide the exponent by 2. So I'm taking the square root of each of these. 2 divided by 2 would be 1, or x to the first. 4 divided by 2 would be 2, so we get x squared, and this one would turn out to be x to the 5th. So that's some background skills. Now we're going to look at the actual factoring problems. So my first one, x squared minus 9. These are both perfect squares, and it's connected by subtraction. So I set up my two parentheses. I'm going to take the square root of the first term, so the square root of x squared, and which is x, and that goes in the front of both parentheses. And then the square root of 9 is 3. Goes at the end. 1 needs to be positive and 1 needs to be negative. Looking at the next one, both perfect squares connected by subtraction. The square root of 4 is 2. The square root of x squared is x. Make 1 positive and 1 negative. And I always put my positive sign first, but it doesn't matter. You could switch those up, the positive and the negative. I'm going to do one more, and then you should probably try some on your own. So here I have my first one where I have a higher power of x, x to the 6th, and there's also a number with it, but both 4 and x to the 6th are perfect squares. So the square root of 4x to the 6th would be 2x cubed. Square root of 25 is 5. So there's the factoring there. So I would try some. If you need to see one with fractions, you can go forward to that part in the video, but I am going to go through these quickly. So this one would be 4s, and then 9x for the 81x squared, plus and minus. This one, when you have a fraction, to check to see if a fraction is a perfect square, both the numerator and denominator need to be perfect squares. Taking the square root of a fraction, we just take the square root of the numerator, so the square root of 1 is 1, the square root of 4 is 2. So if I go to factor this expression, both parts are perfect squares, so we get x and x, 1/2 and 1/2, and plus or minus. Working kind of quickly through the rest of them. This one would start with a 5, and we would get a plus x over 3 and minus x over 3 when I take the square root of that fraction. Here we have 2/9 x plus 7/3 and minus 7/3. The last one, we have variables in both terms, which is fine. We still have difference of perfect squares. So this is going to be 6x plus 7y minus 7y. So to summarize, this is still factoring. We're still taking expressions that are simplified and breaking them up into products, but it's a different type, and we have to look for a different type of pattern in our expression. The bottom section is going to be either type of factoring or possibly both. And this is really, when I think of getting to factoring, you want to look at things and not necessarily know what's coming. You want to say, well, what's the pattern in this expression, and which type of my factoring can I use? So in my first expression, we always look for GCFs when we're doing these. And I do have one here. So it's when I have to kind of choose, it's always GCF first and then look for other stuff. I do have a GCF of 5 in this one, which would leave me with x squared minus 4 when I divided both terms by 5. Then I notice in this binomial, I have difference of perfect squares. So I'm going to factor that into x plus 2, x minus 2. The 5 always still has to stay in the front, or whatever GCF you have, because we want this final answer to be equivalent to what we started with, just written in a different way as a product versus simplified. So my next one is similar. I have a GCF of 7. And I would actually try this whole section, come back. If you need to watch a little more, you can. This is also difference of perfect squares. So 2x plus 1. Sorry, my plus didn't stick there. 2x plus 1, 2x minus 1. The next one, GCF of 10. And then we have difference of perfect squares. And the next one, I have a GCF of negative 2x. So I have my negative 2x out. And then this is difference of perfect squares again. So x plus 2, x minus 2. The next one is a little more complex. There's no numerical GCF. The 4 and the 25 don't have any common factors, but for the x's and y's, I have an x in common and a y in common. So I'm going to take out x, y. Here, I want to then have 4x squared. My second term, I'll have 25y to the 4th. So from there, this is difference of perfect squares. So this gives me 2x and 2x plus 5y squared minus 5y squared. I just want to go back to the last one. I should have mentioned this. Whenever my first term is negative, to make factoring easier, I always try to take out a negative number so that first term becomes positive. It just makes your factoring a little more recognizable in terms of looking for patterns. The next one is kind of interesting because it looks like I could go straight to difference of perfect squares. And I can, but we're going to see that's not the best way. So if I do difference of perfect squares, this is what I would get. Now, the problem is, in both of these binomials, I also have a GCF now. So I could take out a 2 here. And then in the second section, I could also take out a 2. So my 2 2's, the regular numbers go to the front. So 2 times 2 is 4. And this is, sorry about that, this should be a minus 4 here. Okay, so for that section, this should be minus 4. So that's my final factoring. Now that looks complex and different than what we did before. So the way I'd actually suggest to do that one is to recognize that GCF first. Usually people will stop, at this point and not finish. So it's way better to just get the GCF out in the beginning. So there is a GCF of 4 between 36 and 64. And if you do the problem this way, you're much more likely to get that GCF out if you just take it out first thing, which is why we always say GCF first. Okay, either way will work, but it's a little safer the other way. So our last set of questions, the bottom 3, we're going to continue to work through. I have a GCF this time of x cubed. Now, we've been having a lot of two-steppers, right, where we have to do a difference of perfect squares. 4x minus 25 is almost difference of perfect squares, but it doesn't have an x squared, so 4x is not a perfect square. Okay, so that problem needs to stay. That's as far as I can go. The next one, my GCF is negative 5. Looking at my a's, it's just a to the first, and looking at my b's, it's just b. So in parentheses, I have a 4a minus b squared, and then plus 6b to the 4th. That one, I really know I don't have difference of perfect squares. We do have things we do with trinomials. In a future lesson, it won't work here either, so that one is done. This one, I'm going to section off. No GCFs. I'm going to go right to difference of perfect squares. So I have a 4x squared plus 9 and a 4x squared minus 9. And I really like this problem because it lets me really think about that difference of perfect squares. So this first binomial is done. that is not difference. That's a sum of perfect squares. This second binomial, though, is another difference of perfect squares. So I have to take that part, and to break it down to factor completely, that becomes 2x plus 3, 2x minus 3. Okay, so it is possible to have two difference of perfect squares in a row.